Assalamualaikum Pak Iqbal.
Halo Bu Fit, dari mana Bu Fit nih? Dari rumah, dari kampus?
Dari rumah Pak.
Oh, dari rumah. Oh, ini masih yang background-nya.
Assalamualaikum Pak Iqbal.
Waalaikumsalam warahmatullahi.
Sebentar nih, saya barusan live di YouTube Pak. Oke. Di rumah Pak.
Di rumah? Iya, di rumah aja. Ini baru selesai lihat ngawasin anak-anak PAS.
Oh, udah ini ya Pak, apa?
Akhir semester.
Iya, akhir semester.
Kalau yang minggu kemarin sampai mana, Fit, itu Prof Naresnya? Cuma karbonil aja atau dengan alkena juga?
Minggu lalu belum Pak, belum masuk ke apa namanya?
Alkenanya belum masuk.
Iya.
Hai Widya.
Hi, Professor Naresh, how are you?
Good, thanks.
Yeah, I'm sorry, I just read your email.
Oh, that's okay.
So yeah, I'm trying to working on the graphical abstract right now.
I think by tomorrow should be fine. Tomorrow morning.
So I think one thing that I want to make sure, the abstract itself, is it the same with the one that I wrote in the manuscript, or it's more concise?
No, I think you just need pictorial abstract, graphical
Okay.
abstract, and just the structures. I think I'll send you an example of that in the second email.
All right, let me check that.
Oh, sorry, I didn't send it to you actually. I just forwarded it now. Sorry.
Yeah, the second one is the spectra,
I think,
the NMR spectra.
Yeah. I think what happened was that I accidentally sent that email to David and myself, and I didn't send it to you. I'll send it now.
All right, thank you.
Okay.
And we have Pak Iqbal right now, Professor Naresh, who will be our moderator for today's lecture.
Okay.
Okay.
How are you?
Hello, Prof. Naresh. Finally, I can attend your lecture live.
Yep.
So far, I only watch a YouTube channel on our department. So it's the first time.
Okay. Oh, that's good.
Okay.
Yeah.
I think today we will talk about the alkene, right?
Alkenes, yeah.
Yes, alkene, right?
Yeah.
It's an interesting topic since there is a possibility of misconception to the student about alkene.
Yes.
Most of students maybe think that all alkene have isomer geometry, but actually
Right.
not all the alkenes have isomeric geometric.
That's true. That's true.
Yes, it's
Yep. We'll try to keep it simple today if we can.
Okay. Okay. Langsung aja Bu Vidya, atau ada hal yang lain yang mau di?
Sudah Bapak, bisa dibuka barangkali apa ya?
Oke. Oke, selamat sore. Ada Bu Gebi, saya lihat, kemudian ada juga Pak Hayat Solihin, selain Bu Vidya juga ada Bu Amel yang join pada guest lecture kita pada hari ini. Guest lecture kita pada hari ini dengan Prof. Naresh, kita akan berbicara mengenai senyawa-senyawa alkena atau alkin, di mana di senyawa alkin ini atau senyawa alkena ini cukup menarik karena keberadaan isomer geometri. Kita bisa belajar isomer geometri itu kadang kita mempunyai bentuk yang cis dan trans, tapi ada kalanya juga bentuk E dan Z gitu ya. Dan perlu diwaspadai juga bahwa tidak semua senyawa alkena itu mempunyai isomer geometri ya. Jadi ada senyawa-senyawa alkena yang tidak mempunyai isomer geometri. Nah, nanti seperti apa dan bagaimana kita bisa menentukan apakah senyawa alkena itu punya isomer geometri atau tidak, kapan dia pakai sistem cis dan trans, kapan kita pakai E dan Z. Nah, kita akan mendengarkan penjelasan dari mungkin dengan hal-hal yang lain dari Prof. Naresh. maybe it's time to talk about the alkene, Prof. Naresh. I think it's time is yours. Hope everybody can give concentration about this topic of the lecture. Please.
Okay, thanks, Iqbal. I will share my screen so that you can see my slides. And I'll just make it bigger. And I'll get a pen. Yeah. Thank you. So, Selamat sore, everyone. It's afternoon. It's a bit like evening for us, but that's good.
Good afternoon.
Yeah. What I'm gonna do today is continue on the theme of alkenes. We had a little introduction to alkenes in the last lecture, but I'm gonna start from the beginning again, just because there were only a few slides we covered last week. And it's good for new people who are in the audience today. They can understand what we started with last week. We're going to talk about nomenclature first, and then we're going to talk about structure. And after that, we're going to talk about reactivity of alkenes. And as everybody will know, that alkenes are compounds which have a double bond. Some can have more than one double bond, even 3, 4, 5, 6 double bonds. But we're going to concentrate mainly on alkenes with one double bond because it's a first year course and we want to make sure we don't make it too complicated. Okay, let's start with how do we name alkenes? Simple molecules like, where 2 carbons are joined together, they are easy to name because it's just ethylene. But when you have bigger molecules, then how do we start naming them? So one of the things to do when you come to naming the molecules is that you start with the longest carbon chain that is present in the molecule. When we say containing the functional group we're talking about is the double bond. So you look at the longest continuous chain containing the functional group, containing the double bond. And there are 1, 2, 3, 4 examples here. And if you look at the longest chain that is present in the first molecule here is 4 carbon chain. And the 4 carbon chain is, if you look at the alkane with the 4 carbon chain, is butane. Another thing to remember about alkenes is that if a name has "ene" at the end, that "ene" means that the molecule has a double bond. And the first 3 letters or 4 letters tell you how long is the chain length. Say, for example, this molecule here has a carbon length of 4. Similarly, here it has a carbon length of 4. But if you look at this molecule here, it has a carbon length of 6 carbons. And if you look at here, it has an even longer carbon chain. But how do we decide which chain length we should measure? We should measure the chain length containing the double bond. The double bond must be present when you're counting the longest carbon chain. And also you will learn that we have to give the carbon which has the double bond the minimum numbering. It should get the smallest number when you're numbering the carbon chain with the double bond. So the first rule is look for the longest continuous chain containing the double bond, and then you add "ene" at the end. So literally this molecule will be a butene because 4 carbon chain. This will also be a butene because a 4 carbon chain. This one will be a hexene because the 6 carbon chain. So the second rule is that we want to give the functional group the minimum numbering. If you look here, this is 1, 2, 3, 4. But if we count the other way around, then it'll be 1, 2, 3, 4. Then the double bond will start at carbon number 3. But we want to start the carbon with the minimum number. So that means we have to number from this side. and we call that 1-butene. This 1 represents that the double bond starts at carbon number 1. In this molecule here, it doesn't matter whether you start the numbering from this side or the other side. The carbon with the double bond is always present at the 2 position. So we call that molecule 2-butene. In this one here, if you start the numbering from the left-hand side, then the double bond starts at carbon number 2. If we start from the other side, you will see that the double bond is going to be at the 4 position. So that's 3 and that's 4. And we want to give the double bond the minimum numbering. So that's why we start it on this side. And 2 represents the carbon where the double bond is. And hexene means it's a 6-carbon chain compound. Now, if you look at this here, the longest chain that is present in this molecule is 1, 2, 3, 4, 5, 6, 7, 8 carbon. But we don't count it like that. We count it where the double bond is. We have to take into account where the double bond is. And if you count it, then there's only a 6-carbon chain present in this molecule, which is the longest carbon chain. And at the 2 position, there is this group present. And this group is a 3-carbon group, and we call that a propyl group. So the name of this molecule then is 1-hexene because it's a 6-carbon longest chain with the double bond at the 1 position. And at the 2 position, we have this propyl group attached. So we call that 2-propyl 1-hexene. So that's how you number and name the alkenes. What about if the compound has 2 double bonds rather than 1? If there are 2 double bonds present, then we add diene at the end. Di means 2, ene means double bond. So that means got 2 double bonds. Then the rest of the rules are exactly the same. You count the longest carbon chain that is present in the molecule. And then you start with the double bond, which has the minimum numbering. For example, this side, if you start from here, then the double bond starts at carbon 2. But if you start from this end here, like 1, 2, 3, then the double bond starts at the 3 position. So that means we have to start from this side. So the first double bond starts at the 2 position. And the second double bond starts at the 4 position. So it becomes 2, 4, heptadiene. Hepta means 7, 7 carbon long molecule with 2 double bonds. Same here. This one is now a pentadiene, 5 carbon long alkene with 2 double bonds. And it starts from this side because the double bond starts from this carbon. And the second double bond is present at 3 position. So we call that as 1,3-pentadiene. And if you compare it with this molecule here, then this one, the first double bond starts at the 1 position. Second double bond starts at the 4 position. The carbon chain is 5. So it's pentadiene, 5 carbon with 2 double bonds. And 1 and 4 indicate that the double bond starts at the 1 position and the 4 position. Okay, so that's how you name. What if there are both functional group and a substituent present? So the question here is, if you have a double bond as well as a substituent present in the carbon chain, we saw one example of that already. The rule is exactly the same. You just don't worry about the substituent that is attached. You just think about the linear chain longest that is present and giving the double bond the minimum number. So if you look at this molecule here, the longest carbon chain is 5. The minimum number for the carbon is 2, because if you count from the other side, then the double bond will be 1, 2, 3, starts at the 3 position. We want to give it the minimum number. So it starts from the left-hand side being 1. And then it is the 2-pentene because the double bond is at the 2 position. And then it's a 5-carbon chain and it got a double bond. So it's 2-pentene. And after that, you worry about where the substituent is. This substituent is a methyl substituent. It is present at the 4 position. So this molecule becomes 4-methyl-2-pentene. And the same thing applies here. And the same thing applies here. So I want you to think about it yourself carefully. That is that the right way to name this compound? You look at the longest carbon chain that is present. It has 2 double bonds. The double bond starts at the 1 position and 3 position. So it's a 1,3-pentadiene. It's a 5 carbon with 2 double bonds. And then you worry about where the substituent is. And this substituent is methyl. So this is 4-methyl-1,3-pentadiene. Okay. Let's not worry about this structure because this is slightly advanced, but it's still quite easy to do. But I want you to think about these a little bit yourself and then see if the numbering and the naming is correct. The last thing I want to show in terms of numbering is if you have 2 substituents that are present in a molecule, how do you decide how we're going to name these substituents which are present? For example, if there's a chloro present and a bromo present, if there's 2 methyl group present on your alkene, how are we going to name them? How are we going to number these compounds? The first rule always is look for the longest carbon chain where you have a minimum numbering for your double bond. And if you start counting from this end, it's 1, 2, 3, 4, 5, 6, 7. So it's a 7-carbon chain with the double bond starting at 1 position. So this is going to be 1-heptene because hep stands for 7, ene stands for double bond. So it's 1-heptene. Then the question is, you got bromo and chloro. You got a chloro at the 4 position and the bromo at the 5 position. So the question is, should we call it 4 chloro and 5 bromo, or should we call it 5 bromo and 4 chloro? Which way is the correct way? So the way which is the correct way is when these substituents are in alphabetical order. By alphabetical order, we mean A, B, C, D. B comes before C. So A, B, C. B comes before C. So that means bromo will be first, then chloro. It doesn't matter the number, but alphabetically bromo comes first before chloro, and the bromo is present at the 5 position. Chloro is present at the 5 position, and it is a 1-heptene molecule. So that's how you name this compound. And this long molecule here, you might get scared looking at it, how I'm going to name this compound. Don't worry about it. Just look at the longest carbon chain with the double bond that is present. And that's 8 carbon long. And the double bond starts at the 3 position. So that means this molecule is 3-octene. Oct stands for 8 carbons. Ene means a double bond. So it's a 3-octene, double bond starting in the 3 position. Then you're going to see the dimethyl. You got 2 methyl groups. One methyl group is present at the 3 position. Another methyl group is present at the 6 position. So dimethyl, 3,6-dimethyl, because those 2 groups are the same. That's why it becomes dimethyl. The cyclic systems are also easy to number and name. And in the cyclic system, all we need to do is to put cyclo in front of the name. You again look at the longest carbon chain that is present with a functional group. And the longest carbon chain with a functional group is 6, like the ring, cyclohexene, 6 carbon cyclic ring. In the cyclic ring, when you have a double bond, the first carbon is always considered where the double bond is starting. Okay, so it's 1, 2, 3, 4, 5. 4, 5 becomes your dimethyl because there are 2 methyl groups. And cyclohexene means it got a 6-membered ring with 1 double bond. I'm going to leave the other structures for you to try it yourself. You may find it a little bit advanced, but try it anyway. And that's a good way to learn that, that what I am calling, or how I'm using the nomenclature to name and number the alkenes. So try that by yourself and then see how that works out. Okay. All right. So one thing I also want to mention now is you may or may not have heard about omega fats or omega fatty acids. Omega fatty acids are very common in food industry. If you go and buy a loaf of bread from the supermarket, sometimes it says this bread contains omega-3 or omega-6 fatty acids. What do we mean by this omega-3 and omega-6 fatty acids? Fish oil, for example, is also marketed a lot for health benefits. They say, oh, fish oil is really good for us. Fish oil has double bonds present in it. And the double bonds sometimes are donated by this common word called omega. And there's a term that is used which say that this fatty acid is an omega-3 fatty acid, and this fatty acid is an omega-6 fatty acids. And we are told that omega-3 and omega-6 fatty acids are really good for us. And this is something interesting for you to know, that this omega-3 and omega-6 is because of the double bonds that are present in the molecule. This letter omega, represented by this W-like structure, is called omega. Omega comes from Greek alphabet. If you take, like English has A, B, C, D, E, F, G, H, I, J, Greek alphabet starts with alpha, beta, gamma, delta, and the last letter in the Greek alphabet is omega. So in the fatty acid chain that is present, we call the chain which has the methyl group here as the omega end. This is called as the omega end. This is the alpha end. This is the first letter in the alphabet. This is the last letter in the alphabet. So if you look at omega carbon and count where the double bond is present, the double bond starts at the 3 position in this fatty acids. That's why it's called as an omega-3 fatty acid. And if you look at this fatty acid here, this is our omega end. So this side is our omega end. And if you look at the double bond in relation to that omega end, starts at the 6th position. So it's 1, 2, 3, 4, 5, 6. So this fatty acid is called as omega-6 fatty acid. So these omega-6 and omega-3 fatty acids are really good for our health. That's why they're added into food. That's why they also are marketed under fish oil, because fish oil is very rich in omega-3 and omega-6 particularly fatty acids, but it all got to do with the double bond, where the double bond starts from the omega end, that means away from this carboxylic acid, the other end where the number is starting. So that's what is omega-3 and omega-6 fatty acids are, and they're supposed to be good for our health. So if you see next time in the supermarket omega-3 and omega-6, then you will know that they come from the double bond that is present in the molecule. Now, what is the structure of alkenes? So we learned now already that alkenes are compounds which have carbon-carbon double bond. And what makes this molecule so special with the carbon-carbon double bond? So out of that carbon-carbon double bond we have, first of all, remember when you have the carbon-carbon double bond and a carbon substituent attached to it, these 6 carbons here, they are all in the same plane. By same plane, we mean they're flat, like a flat paper. They are like the carbons in that alkene are flat like the paper, two-dimensional flat. And also the carbon-carbon double bond, one bond is what we call a sigma bond, and the other bond, which is a pi bond. And the pi bond is formed by the overlap of p orbitals that are present on this carbon in this manner shown here. So this is a one p orbital, this is another p orbital, and there's an overlap between these two orbitals, and this is what forms the pi bond. So that means the alkene double bond is going to be an electron-rich double bond. And that means there can be a lot of electrophilic addition reactions possible in the case of alkenes, because there's a pi cloud of electrons and it's electron-rich. And that's where it can undergo a lot of electrophilic addition reactions. So that's the general structure of an alkene. And this light blue box here, or rectangle here, represents that all these carbons, this carbon, this carbon, this carbon, this carbon, they are in one plane. They are like the plane of the paper, so to speak. There are also isomers possible in the case of alkenes when you have double bonds. And these isomers are called as cis and trans isomers. The cis and trans isomers are not possible when two substituents on this one of the carbon is exactly the same. So if you look at these two structures here, this carbon has 2 hydrogens present on one carbon. So that means there is no isomer, cis-trans isomer possible in this molecule. This carbon here has 2 methyl groups that also indicate that this compound cannot have cis and trans isomers, because 2 of the substituents on one of the carbon is exactly the same. If that is the case, you won't get any cis-trans isomer. But if the carbon has 2 different substituents, like for example, this molecule here, the carbon has 2 different substituents. There's a methyl, there's a hydrogen. There's a methyl, there's a hydrogen. In this case also, there's methyl, there's a hydrogen, there's a methyl, there's a carbon. There's a methyl and a hydrogen. So in these cases here, where the 2 substituents are not the same on one of the carbons, you can have isomers. So you can have a situation where the 2 groups are on the same side. For example, if you look at hydrogen here, these hydrogens are present on the same side. Or you can say methyls are present on the same side. On the other hand, you can have a situation where the 2 hydrogens are away from each other, are trans to each other. And similarly, methyls are away from each other. So when the 2 hydrogens are away from each other, we call that a trans geometry or a trans isomer. When the 2 groups are on the same side, we call that a cis isomer. And the molecule here is a 4-carbon chain because it is 1, 2, 3, 4-carbon chain molecule. And this one is called as a butene. And the double bond starts at the 2 positions. So this is a 2-butene molecule. Okay. So if the 2 hydrogens on the same side, it's a cis 2-butene. If the 2 hydrogens are away from each other, we call that a trans 2-butene. And remember that if the carbon has similar groups attached to it, or 2 similar groups attached to it, or 2 of the same group attached to it, there is no cis-trans isomer possible. Because if you put hydrogen up, hydrogen down, is going to be the same structure. So I can say, for example, write this structure as hydrogen, hydrogen, and I can write it as a Cl up here and a CH3 down here. These are exactly the same structures. If you compare these two, they are exactly the same structures. The carbon has 2 hydrogens, Cl and CH3. Hydrogen and Cl are together, hydrogen and methyl are together. Hydrogen and Cl are together, hydrogen and methyl are together. So there is no isomers possible when the two groups on the carbon are the same. It's only when the two groups are different, that's where you start to get the cis and trans isomers forming in that reaction. And also remember that cis and trans cannot easily convert into each other. You can't just have a cis molecule and hope that automatically it will change into the trans molecule. It wouldn't. Because in the cis molecule, for example, shown here, if you want to convert that to the trans molecule where you have the 2 hydrogens away from each other, you have to break this pi bond first. You have to break the pi bond, rotate it, and then reunite it. Only then you will get the trans isomer. So it doesn't happen automatically. If you have a cis isomer, it automatically would not change into trans isomer unless you really heat it up a lot. For example, this molecule here is a cis-2-pentene. Why do we call it cis-2-pentene? Because the numbering goes 1, 2, 3, 4, and 5. And the double bond starts at carbon number 2. So it's a 2-pentene, and 2 hydrogens are on the same side. So we call that cis-pentene. If you heat this molecule at 180 degrees Celsius, quite a lot, heat and or shine UV light on it, this HU means UV light, then the cis molecule can convert into the trans molecule where the hydrogens are far away. So the thing to remember is that the cis and trans isomers can be stable by themselves. But if you want to convert one to the other, you need a lot of energy. You have to break the pi bond before you can convert cis into the trans isomer. So remember that. And cis-trans geometry is very, very important. We talked about this conversion from cis double bond to trans double bond when we were talking about imines in the carbonyl compounds. And I told you that the imine formation reaction is involved in vision process. How can we see things with our eyes is because of this rhodopsin compound here, which is an imine, but it also has this cis double bond. This cis double bond is there because there is a hydrogen over here, and there is a hydrogen over here in this molecule. The rest of the double bonds here, they are trans double bonds. So if you look at this one is a trans double bond. The 2 hydrogens are away from each other. This double bond here is cis double bond because the 2 hydrogens are on the same side of the double bond. So when you shine UV light, you will find that the cis double bond converts into the trans double bond. The hydrogen is here now, and the hydrogen is here. So this interconversion between the cis double bond and trans double bond creates a nerve impulse, creates a signal to the brain so the brain can see. So this process is involved in vision, in us seeing things. It's like cis bond getting converted into the trans bond. And that is involved in vision. Also, it's important to note the fats. You know, the fats we consume, there are 3 kinds of fats we consume in our food. One is what we call saturated fatty acids or saturated fats. Saturated means there is no double bond present in the molecule. It's just a straight chain. You can see there's a straight chain. This chain can be 10 to 18 to 20 carbons long, but there is no double bond. We call that saturated fatty acids. So butter, for example, contains a lot of saturated fatty acid. Same is if you look at animal oil, like you get animal fat. Animal fat is also very rich in saturated fatty acids, no double bonds. But we also have what we call unsaturated fatty acids, not saturated, but unsaturated. Unsaturated is another term that is used to show the presence of double bond. Saturated is when there is no double bond. Unsaturated means when there are double bonds present in the molecule, unsaturated. So if there are 3 double bonds present, it's triply unsaturated. And it's interesting to see that the unsaturated fatty acid which exists in nature, like the cooking oil we use, the sunflower oil or canola oil or vegetable oil, they always have cis double bonds. The hydrogen is always present on the same side. So all double bonds present in fatty acids which we eat, they always have a cis double bond. So you can see that 3 double bonds present in this fatty acid, they all cis because the hydrogens are on the same side. And this cis double bond gives this fatty acid like a V-shaped structure. This double bond makes this kink into the molecule and make it look like a V-shaped compound. The third kind of fatty acid that are present, which we eat sometimes, is what we call trans fatty acids. And there the hydrogens are present in opposite direction, cross from each other. This is natural, that occurs naturally. All the unsaturated fatty acid which are present in cooking oil, vegetable oils, they are cis. But some of the cis gets converted to the trans fatty acid. And that happens when you are processing the oil, when the oil is being processed in industry, some of it gets converted into trans fatty acid. And also if you use the oil again and again, like you can use the same oil for frying for many days, some of the cis double bond gets converted into the trans double bond. Because we saw in the last slide that if you heat the cis compound at very high temperature, it gets converted into trans double bond. This is what happens if you take cooking oil and you cook it a lot of times, some of the fatty acid gets converted into the trans fatty acids. And trans fatty acids are bad for us because trans fatty acids they resemble the saturated fatty acid. See, this is the saturated fatty acid, and the trans looks very similar to the saturated fatty acids. And these can block the arteries. They can cause heart disease. The trans fatty acids and too much of saturated fatty acids are not good for us. It's all to do with the double bonds that are present in the molecule. So alkenes are really important compounds in that sense. And cis double bond is very important in food industry because the fats and oils have that cis double bond. But the cis and trans can be sometimes very confusing. Look at these 2 structures here. If I gave you these 2 structures, you can see that in these 2 structures, the carbon has 2 different substituents. This carbon also had 2 different substituents. This carbon has 2 different substituents. This carbon has 2 different substituents. So there are cis and trans isomers possible. So the question might be, which one is cis and which one is trans? Because there is only one hydrogen present. If there were two hydrogen present and two hydrogens were on the same side, we will say that's a cis alkene. Or if the two hydrogens were present across from each other, we call that a trans double bond. But there's only one hydrogen present, so how do we work out whether it's cis or trans? So in the books now, there is another nomenclature used that is called E and Z nomenclature. Instead of calling it cis and trans, you can call it E and Z isomers. This E and Z come from German word. Is German. Z means zusammen. Zusammen means in English together. If something is together, we call that Z or zusammen. If something is opposite or away from each other, we call that antagonon. That means is opposite each other. So that means if two groups are on the same side are together, we call that a Z isomer. And if the two groups are opposite, we call that an E isomer. So instead of calling it cis and trans, you can call it E and Z. But the thing is, how do we find out which group is high priority and which group is low priority? So we need to work out from the structure that which of these groups are high priority. So the rule says that if the two high priority groups, they are on the same side, we call that a Z isomer. And if the two high priority groups are away from each other, we call that an E isomer. But we need to figure out which one is higher priority and which one is lower priority. And typically that priority is to do with the atomic number of the molecule or atomic number of the atom that is present on the carbon. And that's on the next slide. So consider the atomic numbers of the atoms bonded directly to the specific sp2 carbon. There is bromine and there is chlorine and there's methyl as well. But the high priority groups are bromo and chloro because the atomic number of bromine and chlorine is much higher than methyl group, or the hydrogen is obviously one, but the atomic number of bromo and chloro is higher than CH3. So these two groups become the high priority groups. And the high priority groups, if they are present on the same side, like the bromo and the chloro are present on the same side, we call that a Z isomer. And if the two high priority groups are present away from each other, like bromo and chloro, we call that an E isomer. Okay, so nowadays the nomenclature uses more and more E and Z nomenclature rather than cis and trans nomenclature. Let me draw you a structure and try to think whether the double bond that is present, I'm going to talk about the external double bond, not the internal double bond. This is a real molecule. It's a natural product. It is isolated from a marine plant, marine algae. And its chemical structure is there's a hydrogen here and a bromine over here. And it also has a bromine over here. It also have a carbon chain present in this molecule. And it also has a double bond present at this position over here like that. That's the structure of the molecule. What I want you to find out for me is that this double bond, which I just circled, is that a Z double bond or is that a E double bond? So I want you to think about this double bond in isolation. So I'm just going to draw it by itself. So there's a double bond here. On one side, it got a hydrogen. On the other side, it got a bromine just down here. And on this side, it got an oxygen. There's an oxygen over here. And this side, we got a carbon attached to a double bond. So I wouldn't draw the double bond. I'll just say a carbon here. So is this compound here, the double bond here, is that a Z isomer or is that a E isomer? I want you to think about it for 2 minutes. And if somebody knows the answer, they can put in the chat whether they like it as a Z isomer or an E isomer. And then we can discuss.
Yuk, silakan mahasiswa dijawab kira-kira apakah dia Z ataukah E isomer geometrinya.
Think of the priority and think of, I think one answer. Oh yeah, we got one answer already, and that's the correct answer. 2 answers, 3 answers now. Okay, we got the correct answer. Thank you, everyone. Thank you, thank you, thank you. Because in terms of atomic number, oxygen and bromine, they have a higher atomic number than hydrogen and carbon. So that means these 2 groups are high priority, and the high priority groups are on the same side. So if high priority groups are on the same side, then it's a Z isomer. So that's well done, because this is actually a real molecule, and you figured out that it is a Z isomer. Excellent, well done. All right, now let's get ready, set for the chemical reactions involving alkenes. And I told you already that alkenes are electron rich. There's a pi cloud, there's a pi bond present here. And that means it's going to undergo electrophilic addition reactions. So that means it's going to, the electrophile is going to add onto that double bond, or the double bond is going to attack the electrophile. Electrophile is species that love electrons, and you can imagine that in HBr, if you have acid, you're going to have a H plus species present, and you're going to have a Br minus species present. And H plus is electrophile. It loves electrons, and electron pair here will attack this H plus to add that hydrogen onto the double bond. And because you are giving away a pair of electrons, you're going to get a positive charge on one of the carbons. So the electrophile adds to an sp2 carbon of the alkene. This is your electrophile, is positive. Electrophile means something which loves electron, something which loves negative charge. And H plus loves electrons because positively charged, so it loves electrons. That means it's going to add to that sp2 carbon, and when you add that H plus to the this carbon here, one of the carbons is going to get a positive charge because the pair of electrons is gone now. And then we call that carbon which is positive a carbocation. Carbo means carbon, cation means positively charged intermediate. So there is a positive charge, and then you have a Br minus present as well from the HBr. And the Br minus then adds on to the carbon plus, and you get the addition of HBr across that carbon-carbon double bond. And we call that electrophilic addition of alkenes. So that means an electrophile has added onto the double bond. Okay, that's a general reaction. So the first step is slow. The first step happens slowly, but the second step is really fast. The bromine minus coming and attaching onto that carbon. Let's simplify that a little bit more. This is just an introduction that we're going to add acids to the alkenes. So let's make it a little simpler. So this reaction of electrophiles, this HX can be HCl. So HX is a general term for halogen, so it can be HCl. It can be HBr. and it can be even Hi. Okay, so it can be even Hi. I want you to think about also, will Hcn do the same reaction? We'll come back to that later, but I want you to think in your mind, will Hcn will do the same reaction? At the moment, we're just talking about HCl, HBr, and Hi. So that's a typical reaction. You take a simplest alkene, and this alkene here, can somebody tell me the real name of this molecule? This molecule is just 2 carbon with a double bond. And what will be the name of this molecule here? Very easy. We've done it before. Ethylene. It'll be ethylene or ethene. That's very good. Thank you. So because it's 2 carbon chain, it's ethane, ethene. You can call that ethene. And the numbering will always be 1, so we don't have to define the numbering. So this is the simplest possible alkene. You add HBr to it, and the product you will get will be where the hydrogen and the bromine has added to the double bond. And we call that addition of HBr to the ethylene or ethene. And this is an example, electrophilic addition. HBr and all halogen acids act as electrophiles. So all these HCl, HBr, Hi, they will act as electrophiles. So simple. Even make it more simple. Why HBr is electrophilic? Why HBr is electrophilic? The reason why HBr is electrophilic is that if you look at the electronegativity of the 2 atoms, H and Br, are very different. Br is much more electronegative than H. So that means the bond is polar. So this bond is polarized bond. That means the electron distribution in this molecule here is unsymmetrical. Br has the negative, more electrons, and H plus has less electron distribution. The electron distribution is more towards Br minus. One end of the polar bond is electron deficient and can be considered as an electrophile. So H here can be considered as an electrophile because this is electron deficient. Or even in some cases, it is ionized. It is present in the form of H plus and Br minus. But there is a big electronegativity difference between hydrogen and bromine. The electron distribution is more towards Br minus because it's more electronegative. Hydrogen is electron deficient, so it has a positive charge, and that's why it acts as electrophilic molecule or electrophile. It loves to get more electrons if it can. But how electrophile react with alkene? And as I told you just now, the carbon-carbon double bond is an electron-rich double bond. It is electron-rich because the double bond is made up of a sigma bond and a pi bond. And pi bond is just the overlap of the p orbitals in the molecule. And the pi orbital offers greater electron density. There's a lot of electron density present in that pi bond. And that means the electrophile can access that electron density quite easily. And this electron density is located above and below the plane of the double bond. So if you imagine that the double bond is like a plain paper, the electron density is up here, and the electron density is down here, the pi bond on top and the pi bond at the bottom. That means the electrophile can come quite easily and add onto that pi cloud which we have, which is located above and below the plane of the double bond. How does the reaction occurs? The reaction usually takes place in 2 steps, like we saw in the first slide. It can, one reaction can be fast and one can be slow. there are two elementary reactions. One is the addition of a proton to the pi bond, giving a carbocation. And that's what we saw in our first reaction slide. The first reaction slide was that the proton adds to the pi bond to give a carbon with a positive. We call that carbocation. And the second one is the reaction of the carbocation with the bromide. So in the first step, there is the addition of H plus onto the double bond. And second one is the attack of the bromine minus onto the carbocation to give you the product. The first step is slow and the second step is faster. And the slow step is always the rate limiting step. Whichever step is slow is going to be the rate limiting step. I can give you an example of a factory making cars. They can assemble the car very quickly, but putting the steering wheel is the slowest part. There is only limited supply of steering wheel, and the steering wheel is the slowest part you can put on the car. So the production of the car, how many cars you can make in that factory, are going to depend upon how many steering wheels you have. And steering wheel is the slowest step. So the slowest step always determine the rate of a reaction. Okay, so this is always a rate limiting step. So this is also, I explained it to you on the very first slide, that this is what happens. That in the first step, you get the addition of H plus onto the carbon-carbon double bond to give you a carbocation. This is the slow step. And then the second step, the Br minus reacts with that carbocation to give you the product. And this is your fast steps. And the slow step here is the rate determining step that determines at what rate the reaction will take place. Okay, so this is represented again. The double bond reacts with HBr, give you carbocation, and the carbocation will then be attacked by the Br minus. Note, removing the electrons from the pi bonds leave one carbon electron deficient. Because you remove the electron cloud, you make one carbon deficient, and that carbon becomes carbon positive, and we call that a carbocation. And then the carbocation will be attacked by this Br minus. Because this minus, it is a nucleophile. Nucleo is positive. Philic means something which loves positive charge, and bromine is nucleophilic. Br minus is nucleophilic. It loves positive charge. So it attacks that carbon, form that carbon bromine double bond, and the product is neutral. And look at all the valency rules, they are obeyed. That means all the bonds are formed as they should. Carbon has 4 bonds attached to it. Hydrogen has 1, and bromide has 1. So this is, in the simplest terms, how you can explain the addition of hydrogen halides to the corresponding double bond. Now, what if the alkene you had is unsymmetrical? So what we saw in the last example was a reaction where you had the double bond and the 2 carbons were the same, and you had the hydrogen here and a hydrogen here and a hydrogen here and a hydrogen here. That was our simple alkene molecule, and it was symmetrical. This carbon is same as that. So addition to symmetrical alkenes such as ethene, ethene is an example here. Cyclohexene is another one mentioned here, which is basically this molecule here, cyclohexene. That's a symmetrical molecule. And 2-butene is basically carbon CH double bond CH CH3. That's the 2-butene, is also symmetrical because both sides are are the same. You can have CH3 here, and it's a symmetrical molecule, but there is one catch to it. When we come to cis and trans, you will see some interesting reaction. But they can only give one structural isomer. You can only get one product out of ethene, one product out of cyclohexene, and a product from the butene as well. I won't go into the stereochemistry at the moment. We'll come back to that later. What if the alkenes were non-symmetrically substituted, such as propene? What if your alkene has this structure? You got a carbon, you got a hydrogen, and you got a hydrogen, and you have a CH here, and you got a, I should draw it actually. So you have a CH3 over here, and you have a hydrogen over here. So now this carbon is different from this carbon over here. Here, the two carbons were the same. So you only got one product in this reaction. But if you have a non-symmetrical alkene, it can give rise to two structural isomers. You can get two products out of this reaction, because you can imagine the hydrogen can add here and the bromide can add here, or the bromide can add here and the hydrogen can add here. So there are two structural isomers possible in this scenario. But we don't. We only get one product out of these reactions. And the second isomer which is formed may be a very minor byproduct of that reaction. So why that is so? Why do we get only one possible product from that reaction? Why don't we get two? And that is shown here. The two possible products in this reaction, if you add HCl to it, you will get a product where the chlorine is present in the middle, or you will get a product where the chlorine in this case will be present CH3. So the second possible product will be, you can get a CH2, Cl. There are two possible products in this reaction. Okay. But however, there's only one product that is observed in the reaction, although there are two possible products. You can imagine if HCl adds, you can imagine that the hydrogen has gone to the CH2 plus. That will be the intermediate cation that is formed. And if this H plus goes to the middle carbon over here, then this CH2 is going to get plus, and this is the carbocation here, which is going to give you this particular product. So how do we figure it out? Which is the product that is going to be formed? And is there going to be only one product, or is going to be two products in this reaction? But I can tell you there is always one major product formed in this reaction, which is this product here. The main reason why you get only one product in this reaction via this CH3, CH3 plus, the middle carbon here is what we call a secondary cation. We've been talking about primary and secondary for some time now. We said that whenever a group has just one hydrogen, we call that a secondary group. It can be a secondary alcohol, it can be a secondary amine, it can be a secondary amide, it can be any one of those. So this is the way I'm drawing that carbocation. You can see that the central carbon has got one hydrogen. So we call that a secondary carbocation. In the case of this one here at the end, you have a hydrogen here and a hydrogen here. So it got two hydrogens on that carbon, and we call that a secondary carbocation. Sorry, a primary carbocation, because it has two hydrogen present on that carbon. So if there are 2 hydrogens present at that carbon, we call that a primary carbocation. And if there is only 1 hydrogen present, we call that a secondary carbocation. And secondary carbocations, the tertiary carbocations, they are more stable than the primary carbocation. If this carbocation is more stable, then this will be the carbocation that will be formed, and that will lead to the product. And hence, that's the major product we get from this reaction. I just overwritten on some of the things here, which I want to rub off so that we can see what's underneath. So this is another example here, 2 examples here actually, where the alkene is unsymmetrical. So you can see this double bond here is unsymmetrical. You have a hydrogen methyl on this side and a methyl on this side. So I can draw that again for you so that it's a bit easier. So it has a CH3 here, a CH3 over here, and then you have, excuse me, the writing because it's a bit hard to draw with the writing pad, a CH3 over here like that. So this is this structure over here. Maybe ask you one more question. Can this compound or this compound here, can they have cis and trans isomers? So I'm asking you guys a question, can this alkene and this alkene have cis or trans isomer? Just answer yes or no. You can answer in the chat whether it's a yes or no. Can this have cis and trans isomer? Can this have cis and trans isomer? And if the answer is no, why is that? Why doesn't this molecule here can have cis and trans isomers? So the answer I got was that this compound and this compound cannot have cis and trans isomers, which is correct. So the question is why this molecule here cannot have cis and trans isomer?
Yep, alasannya kenapa?
Yep, sorry.
Ryan?
You can write in the chat or I can.
Maybe direct.
Maybe they are same. These 2 groups are the same. If the 2 groups are the same on that carbon, then you can't have isomer. So there's no isomer possible. And if you, but they are unsymmetrical. They are not symmetrical compound. They are unsymmetrical. And there are 2 products possible in this reaction. You can imagine that the hydrogen can go here on this carbon. So if I write it like this, hydrogen and iodide like that. So in this reaction, hydrogen cannot go on this carbon and iodide can go on this carbon. Then you will get this product. And if I write it like that, iodide over this side and and hydrogen on this side over here, then you can get the second product. Then you can get this product over here. So the question is, this is the major product and this is the minor product. So this product is preferred over this product here. So what is the reason for that? Why do we get this as a major product and this as a minor product? Similarly here, you can have HBr reacting in this manner. You can have bromine over here and hydrogen over there. So hydrogen goes here, bromine goes over there, you get this product. But you can have the other way around. You can have hydrogen over here and bromine on this side, and you will get this product. But this is the major product and this is the minor product. Why is that? Why this is the major product? The answer lies in the carbocation intermediate that is formed in this reaction. This compound here is formed by the tertiary carbocation. By tertiary carbocation, I mean I'm concentrating on this carbon in the center. So you have a carbon with a methyl group at the top, right? And you have another methyl group on that side. And you have a CH2, CH3 group on this side. So you have a CH2, a CH3 group. I wouldn't draw that. So the intermediate is going to be a carbocation, which looks like this. We call that a tertiary carbocation, T-E-R-T, tertiary carbocation, because the 3 carbons attach to the central carbon atom. If you look at this carbon here, then this carbon has a CH3 group attached on one side, right? You have a hydrogen attached over there, and you have a carbon substituent attached on this side. Whatever that carbon substituent is, doesn't matter. And you have a positive charge here. So this carbocation here has got 1 hydrogen and 2 carbons. This is what we call a secondary carbocation. The tertiary carbocation is always more stable than the secondary carbocation or primary carbocation. That's why this is the product that is formed. And the same thing applies here. The carbocation which gives the major product is a tertiary carbocation. So there is a cyclohexane present here. There is a methyl present here, and this is your positive charge. So this is your carbocation. And this is the tertiary carbocation. There are 3 carbon groups. So that's why you get that as a major product. And this gives rise to a rule which we call a Markovnikov's rule. The Markovnikov's rule says that the addition of a hydrogen halide, it can be HBr, it can be HCl, it can be Hi, to an alkene occurs such that the hydrogen forms a bond to the sp2 carbon that already has the most hydrogens directly attached to it. So that means if you look at this structure here, you look at the carbon which has the most number of hydrogen attached to it. Is this one here. If you call that, if you look at this double bond, this carbon has 2 hydrogens attached to it. This carbon has methyl attached to it. So clearly this carbon is the winner because it has the most number of hydrogens attached to it. So according to this rule here, the hydrogen from the HCl, HBr, or Hi will add onto the carbon which has higher number of hydrogens, or the most number of hydrogens. So there are most number of hydrogens present on this carbon. So that means that hydrogen here will add on to that carbon. It becomes a CH3. See, the CH2 has become a CH3. The hydrogen got added here. And the Cl or Br or iodide will add to the second carbon over there. And this is what we call a Markovnikov's rule. In all Markovnikov rule reaction, the hydrogen plus goes to the carbon, which has the most number of hydrogens attached directly to it. The reason is, like I was telling you just now, the carbocation, stability of the carbocation. If the carbocation is more stable, is more likely to form, it's going to be more happy, and that's why it's favored that way. And we learned just now what are tertiary carbocations, what are secondary carbocations, what are primary carbocations, and you can also have a methyl carbocation which just got 3 hydrogens attached to it. The tertiary carbocation is always much more stable than the secondary cation, primary cation, and methyl cation. So that means this is going to form much more readily than this one and this one and this one. Now, the question I'm going to ask you guys is why a tertiary carbocation is more stable than the primary or the secondary carbocation. So what I'm asking is that, what I'm saying is that this tertiary carbocation is much more stable than the secondary, than the primary, than the methyl. But why a tertiary carbocation is more stable than the primary carbocation, for example? Any ideas, any suggestions you can write in chat. There's one answer already good. Effect of hyperconjugation. Yes, one is hyperconjugation. That's a very good answer. But there's another answer. What is the nature of the methyl group? What does methyl group normally does? Is it electron donating or is it electron withdrawing? What is the nature of methyl group? The methyl group is electron donating. Good, excellent. So if a methyl group is electron donating, you have 3 methyl group attached to carbon with the positive charge. This positive charge is going to be stabilized because the methyl is putting in electrons, electron donating group, stabilizing the positive charge. So that's why the tertiary carbocations are always stable than a primary cation, for example. That's a very good answer. I like that. Okay, let's move on. So now that explains the reaction. If we look at this reaction again of a butene reacting with HCl, you have a carbon which got 2 methyl groups attached, you have a carbon which got 2 hydrogen group attached. And we know from our Markovnikov's rule that this hydrogen plus here is going to attach to the carbon which has 2 hydrogens because that got the most number of hydrogens. So if this hydrogen attaches here, you're going to generate 2 possible carbocations. So if hydrogen attaches to this terminal CH2, which Markovnikov rule says is going to attach here, you're going to generate a tertiary carbocation. If it attaches to the carbon over here, then this CH2 is going to come plus, and this is your primary carbocation. And we learned already now that the tertiary carbocations are more stable, they are of lower energy, and hence they are formed in preference. And then the Cl minus can react with that carbocation to give you the only one product you're going to get from that reaction. Okay, so by knowing the Markovnikov's rule, you can predict what product is going to be the major product in your reaction and how that is going to form. So that's what we learned. So there is, you can slightly modify the Markovnikov's rule and talk about it in terms of a mechanism version rather than the initial version. So initial version was that addition of a hydrogen halide to an alkene occurs such that hydrogen forms a bond to the sp2 carbon that already has the most hydrogens directly attached to it. This is what we learned, general Markovnikov's rule. But you can modify this Markovnikov rule and say addition of hydrogen halide to an alkene occurs such that initial protonation occurs to give you the most stable carbocation intermediate. So you can define the Markovnikov's rule in 2 ways. One, you can say, okay, the hydrogen adds to the carbon which has got the most number of hydrogen already attached to it. You can say the addition of hydrogen halide occurs in such a way that the initial protonation, initial reaction with H plus gives the most stable carbocation because it is the carbocation which is determining which product is formed in the reaction. What about the stereochemistry? We didn't talk about stereochemistry at all. So all the examples we looked at so far were where the products did not have a chiral center, where the product were quite simple. So for example, reaction of on an alkene, if you react, say, C double bond, the simple molecule at ethene or ethylene, you react that with HBr, you don't get any stereoisomers, you don't get any chiral center forming, you just get the formation of this ethyl bromide here. And you can see this carbon has 2 same substituents attached. This carbon has 3 same substituents attached. So there is no stereochemical consequence. That means the carbon does not have a chiral center. What about if we take the example of 2-butene? What's going to happen? The 2-butene I have drawn here, I'm saying that this butene can be cis or trans and you will get the same result. Let's just draw it with cis first, and then we can draw it with trans and then see if we get the same result. Now, what's going to happen to Markovnikov's rule? Because Markovnikov's rule said that the hydrogen from the HBr will attach to the carbon which has most number of hydrogens. But if you look at this structure, the 2 carbons, they have the same number of hydrogens. But it's a symmetrical molecule. It doesn't matter whether you add hydrogen here or on this side, you get the same carbocation. So if I add it over here, I get a carbocation this way. But if I added it the other way, I will get C plus, will get hydrogen, and I will have CH3 here. And I will have a CH2, I'm just going to write it just like that, hydrogen here, and a CH3 over here, right? These 2 are exactly the same compound, right? This one and this one are the same because the substitution are the same, because that they're equal substitution with carbon. Okay, so that's the first step. H plus added onto the carbon. And then the Br minus is going to attack the methyl group. The bromide here reacts with the secondary carbocation to give the product. So bromine adds there. But what are the consequences? If you look at this carbon here, you got a bromide, you got a hydrogen, you got a CH3 and a carbon. So this central carbon here is a chiral carbon. It got an optical center because the 4 substituents are different, and it's an sp3 carbon. So there's a bromide here, there's a hydrogen here, then you have a CH3 at the bottom here, and then you have another then you have another carbon on this side. So there are 4 different substituents attached to the central carbon. So there is a stereochemical consequence in this reaction. So the question is, are we going to get 1 stereoisomer forming, or are we going to get 2 stereoisomer forming in this reaction? Let's see. One thing to remember is that the carbocations, like the double bond, they are sp2 hybridized. And sp2 hybridization structures, they are described as trigonal and they are planar. So the carbocation here is an sp2 hybridized carbon, and it is trigonal planar structure. By trigonal planar structure, we mean, as I told you, planar is like a paper, like the hand here is planar. So if the carbocation, you can imagine the carbocation is sitting in the center of my palm, and the bromide minus is going to come. The bromide minus can come from the top of my hand, or the bromide minus can come from the bottom of my hand, because this is planar. The carbocation is planar, like a paper, and the bromide minus can attack from above the paper, or it can attack from below the paper. And the possibility of it attacking from the top and the bottom are exactly the same. 50% can attack from the top, and 50% can attack from the bottom. As is shown in this slide, the Br minus can attack from the top, or it can attack from below. And if it attacks from the top, the Br goes up there. If it attacks from the bottom, the Br goes under there. And that gives 50-50 mixture of these two compounds. By a racemic mixture, we mean it's a 50-50 mixture of the two enantiomer. That 50% is one enantiomer and 50% is the other enantiomer. And you can work out whether it is S or R by following the standard nomenclature for defining an S chiral center or an R chiral center. Is it clear to everybody why we are getting this 50-50 mixture? And 50-50 mixture is called as a racemic mixture. I hope you have done some stereochemistry before. And stereochemistry is when you have 50-50% of the two enantiomers. Enantiomers are compounds which are mirror image of each other. If I put a mirror here in the middle, the enantiomeric compounds are mirror image of each other, but they are non-superimposable mirror images. Like I told you last time, the two palms of our hand, two palms, you cannot superimpose because thumb is on this side and the thumb is on this side. This is what we call non-superimposable mirror images. They are like mirror images of each other, but they are non-superimposable. We can't put one hand on top of the other. And that's what I mean by racemic mixture. When you got 50-50 mixture of two enantiomers, we call that a racemic mixture. Let's see. Now, let me ask you a question then at the back. We said cis or trans will give the same result. What if the double bond was a trans double bond rather than a cis double bond? Will it make any difference to the product? If your starting alkene was a CH3 here and a CH3 over here, and the hydrogen was here and the hydrogen was here, drawn in a trans manner, then the question is, will it make any difference? We said cis or trans, same result. It wouldn't make any difference because in the intermediate here, there is no more double bond present, and carbon-carbon single bond has a freedom of rotation. That means this single bond can rotate freely. If it can rotate freely, there is no cis and trans left anymore in your intermediate structure. So it doesn't matter if you start with cis or trans. The cis and trans are only there because of the double bond. If the double bond is gone, like in the intermediate here, then there's no more cis and trans left. Okay, so it's not going to make any difference. But one question I might still ask you is, while we are here, before we go to the water, maybe I just draw it somewhere here again. What if I say we have this alkene? Just trying to check if you are still awake. CH3 here. What if we add HBr to this compound? There are two possible products. HBr. One possible product you might get is double bond. You can have a CH3 over here. And you can, oops, sorry, something happened to my slide. Oops. Oh, I'm going the wrong way. Oh, yeah, sorry. Sorry about that. It's just moved away. CH3Br here. And the second product you can get from this reaction will be where you will have the CH3 over here, and you will have, sorry, excuse the CH3 because it's hard to draw with pad. So there are two products possible. One is product A, I call that A, and one is product, stop. One is product B. So the question to you is that which will be the major product in this reaction? Will it be A or will it be B? So out of the two products possible, A and B, which is the major product? The answer is quicker than I can think. It's A. Excellent. That's good. Why will A be the major product? So everybody said A will be the major product. And then my next question is, are there any enantiomers possible in compound A? Yes or no? So this compound, can it have enantiomers? Yes or no? Okay, the answer to the first question was Markovnikov's rule. Yeah. What about in the case of carbocations? Answer, tertiary carbocation. Excellent, thank you. So can this compound has enantiomers or not? Compound A? Again, yes or no? Is there enantiomers possible for compound A? Can we have a mirror image which is non-superimposable? Everybody's gone quiet. That's a very simple question. Are there enantiomers possible for compound A?
Remember, if we talk about enantiomer, we have to chiral carbon. Can you see there is a chiral carbon there or no? So you can say we have enantiomer or no. Ayo dijawab.
That's a good hint. Make it easier. Look at this carbon here and see what groups are attached on that carbon. There's a methyl, there's bromide. This side has a CH2. There's a hydrogen here and a hydrogen here. And the other side also have a CH2. That group is the same. So the two groups are the same. So if two groups are same, you can't have four different groups attached to that carbon. So that means this cannot have mirror image non-superimposable. So there's no chiral center present in this molecule. What if I had instead of that hydrogen here, there was another methyl group present. If there was another methyl group present here, then you will have two different groups attached to that carbon over here, because that's CH2, that's CH3. So this is different from this one. So then you will have a chiral center, but not with this compound over here. Okay, good. Let's move on. How are we going for time? All right, we got about 8 minutes left.
Yes.
I'm happy to leave the 8 minutes for questions if you like. And if anybody has any questions, I'm happy to answer rather than start a new reaction. But it's entirely up to people.
Oke, silakan ada yang mau bertanya?
Mungkin saya Pak boleh?
Silakan, langsung aja.
Otherwise, I can ask another question if you like.
There's one I think Rian will be ask you about something, Prof. Naresh.
Which one? The
Rian. Ryan?
Ryan.
Yeah, Ryan.
Ryan, please.
I think she just mentioned tertiary carbocation. That was the answer to last question, I think.
Yeah.
Markovnikov's rule and tertiary carbocation. Yeah, that was the correct answer.
Okay, thank you, Prof. Okay. My question is,
Yep.
what if the carbocation in the alkene is a tertiary carbocation? Will the reaction still be fast if we adding with Br2? Okay, so maybe it's a little hard for me to
Sorry, I didn't quite understand the question.
Reaction with Br2?
Mungkin
Br2, sorry, reaction with Br2. Sorry, you're asking for reaction with Br2?
Yes, there is
okay,
two step, right? So in step 2 is fast rate.
Oh, okay. So the question is whether we have still a slow and a fast reaction in the case of bromine.
Yeah.
The bromine happens in a different way. So actually you have to wait till the next lecture. You actually started asking the question from the next reaction, because in the next week tomorrow we will look at the addition of halogens to the double bond. So we will answer that question tomorrow. Yeah, that's a good question, but we'll cover that tomorrow. Because we will look at the, we will look at the, you're going faster than me. We will look at the additions of water tomorrow and addition of halogens tomorrow, and also hydrogenation tomorrow as well, addition of hydrogen to the double bond. That's another important reaction. Maybe I can ask you guys, oh, sorry, there's a question in the chat. Oh, okay, that's all right, no worries. Maybe I can ask you the same question on the other slide we had. Or maybe I can ask a question. Say if we have a structure which looks like this. Say if I make a 5-membered ring, if somebody gave you a 5-membered ring like that, and gave you this double bond over here and asked you to react this with HBr or HI maybe, what will be the product of this reaction? So a simple question, we want to react that compound with HI, and what will be the product of that reaction? So there are 2 products possible again. And actually I wanted you guys to draw the answer for me, but I don't think you can draw the answer in the chat box. You can only say yes or no. So the 2 possible products are, you can have a CH3 over here like that, right? And you can have an iodide going here like that, or you can get a 5-membered ring. So like that, you can have a CH2 with the iodide here. So you can have a CH2, sorry, oops, excuse me. Oh, where did it go? Oh, you can have a CH2 and an iodide attached to it, and have a hydrogen over here. So these are the 2 possible products. This is one, this is the second, CH2I and H. So if we call that A and call that B, then the question is, what will be the product, which will be the major product in this reaction, A and B? Will it be A or will it be B? What would be the product of that reaction?
Kira-kira apa tuh? A atau B?
Anybody in the chat? Oh, nobody in the
Not-
chat.
Not yet.
Yet. Okay, let's see.
Prof. Naresh, maybe you can explain later maybe about 1,2-ship product. If we have secondary carbon carbocation, it will be give another product beside the
Yes, so if you
two-
have a secondary carbocation, you might get a mixture, right? Say, for example, I'm just checking if we have an example. Say if you have I think there was a reaction where we had so like this one here. So this gives a secondary carbocation versus a primary carbocation. So in this case, again, the secondary carbocation product will predominate, and then the primary one will be less or will be minor product formed in this reaction, but the secondary carbocation is more stable than a primary carbocation. So that's why you get this product more than the other. But coming back to the question which I had just now, here, this will be the major product and this will be the minor product. The reason is that the carbocation, which is tertiary carbocation, which is more stable, is the one which will have a CH3 there and a positive charge in that carbon in the middle. So that's your CH3 attached to it. And the second carbocation, which is there, if you see, that has a CH2 plus on it. This is CH2 plus. That's why this is like a primary carbocation. And tertiary carbocation is much more stable than primary carbocation, and that's why this product will form. When there is nothing written here on the carbon, it means that there are 2 hydrogens present on that carbon. Sometime in chemistry, the hydrogens are not written down in the structure, and it is assumed that the 2 hydrogens are present on that carbon. So that's why you get this as the major product in this reaction. Okay. Okay, while we are coming to the end, I just want you to think about this reaction, which we're going to cover tomorrow. Instead of, sorry, one thing I mentioned earlier was that why HCN doesn't react. We talked about reaction of HCl, HBr, and hydroiodic acid, but we said that the HCN doesn't undergo that reaction, and we can probably talk about that now. The Hcn hydrocyanic acid is a very weak acid compared to HCl. If you compare HCl to HBr and HI, Hcn is a very, very weak acid. The pKa value is only 9.2. So it isn't acidic enough to do the initial protonation reaction, because the first step in the addition to the alkenes was the reaction of H+. But in the case of HCN, because it's a weak acid, it cannot give away that HCl. It is very little ionized under normal pH conditions. So that means you will need a catalytic quantity of an acid. Doesn't work. HCN in the reaction does not dissociate sufficiently to generate any cyanide in the second step. So that means HCN, if you write the equilibrium for HCN, it lies towards the left-hand side rather than a right-hand side. So the equilibrium is more towards that side. So there's a very little H plus and Cn present, sorry, Cn minus present in HCN. So there is very little cyanide present in that reaction. So that's why HCN doesn't add across to double bonds. If you take alkenes and then try to react with HCN, you get no reaction. The reason is that Hcn is a very weak acid, and it cannot do the initial H plus addition onto the double bond. And if that cannot do, then the Cn cannot add. So that's why the reaction doesn't work. Okay, so that's the reason why Hcn doesn't work. But we'll look at water, halogens, and hydrogenation in tomorrow's lecture.
Okay.
All right.
Okay. Any question? Any other question? No. If
Oh, there is something.
there is one question from Ryan, please.
Yeah.
Sebelumnya Pak, mohon maaf kalau misalnya pakai bahasa Indonesia atau harus pakai bahasa Inggris Pak?
Pakai bahasa Indonesia boleh.
Boleh ya Pak. Jadi intinya gini, tadi ada di salah satu slide di mana ketika direaksikan dengan HBr, BR-nya itu kan hanya itu terikat dulu pada C, sehingga C yang satunya lagi akan menjadi karbokation. Nah, hanya saja kalau tadi itu karbokationnya adalah primer. Nah, apakah ketika karbokationnya itu tersier, ketika akan bereaksi dengan Br-nya, dia akan lebih lambat gitu, karena tersier itu kan lebih stabil gitu Pak. Jadi kalau tadi itu yang primernya itu sangat cepat, fast gitu. Bagaimana Pak?
Kecepatan reaksi antara.
Iya, kecepatan reaksi.
Kecepatan reaksi antara
BR dengan
terhadap karbokation primer dan karbokation tersier begitu.
Iya, ya Pak. Bisa dibilang seperti itu.
He asked about the reaction about Br minus to primer carbocation and tertiary carbocation.
Yeah.
Which one will be more fast than the other?
Okay, so when you are looking at the reactions like that, the intermediate, which is very, very unstable, is going to be more reactive than the intermediate, which is more stable. So if some intermediate is very unstable, it will react very quickly because it's very unstable. And if an intermediate is very stable, then it will react slowly. So in that case, say methyl carbocation, which is very unstable, will react very, very quickly. And tertiary carbocation, which is much more stable, it will react much more slowly. Say, for example, the tertiary carbocation can do another reaction, which is, say, not possible in the case of methyl carbocation. So if you have, if I have a tertiary carbocation like this with a positive charge here, and there is a methyl group at the top, right? And there's a methyl over here. And if there is a C, if I write another methyl as a CH, like that, and like that, what can happen, because this carbocation is so stable, it can do this reaction. This pair of electron can move here. So you can get C double bond CH2, and you will have a CH3 over here and a CH3 over here, like that. Because the tertiary carbocation is very stable, it can do a side reaction. While if you just have a primary carbocation, because it's very unstable, it will react very quickly. It wouldn't do the side reaction.
Yeah.
So the tertiary carbocation would be slower to react than the primary cation. The other way around.
Okay. Jadi Rian, kalau misalkan saya analogikan gini ya, jadi kalau misalkan kita punya karbokation yang primer, reaksinya bisa berjalan secara cepat, cuma ya produknya menjadi tidak stabil. Tetapi kalau karbokationnya itu tersier, reaksinya berjalan lebih lambat karena kestabilan dari karbokation itu, tetapi produknya menjadi lebih stabil. Gitu. Karena keberadaan dia sebagai ion, karena stabil itu lebih lama. Kalau keberadaan dia sebagai ion itu lebih lama, maka kemungkinan dia untuk bereaksi, menghasilkan produk, itu menjadi lebih mudah. Dibandingkan kalau misalkan karbokation primer, dia cepat bereaksi lagi, artinya keberadaan dia sebagai karbokation itu menjadi sangat cepat. Akibatnya kemungkinan dia bereaksi untuk menghasilkan produk lain itu menjadi sangat sedikit. Makanya produk-produknya menjadi lebih minor dibandingkan yang tersier. Itu kira-kira tambahan. Ya.
Both will be very reactive, but still there is slight difference.
Okay.
Okay, thank
Right.
you, Prof.
Thank you. Okay, I can stop sharing my screen, I think. Yeah. Okay.
Okay. Maybe we will continue about this alkene topic tomorrow.
Yep.
So we can move to another reaction or another structure about the alkene. And then for today, I think it's enough. And
so the plan is that we will finish the alkenes tomorrow, and then we'll start with the alkynes tomorrow as well, hopefully. And then the last lecture next week will be on alkynes. Yeah.
Okay, saya kembalikan ke Bu Vidya kalau begitu, Bu Vidya.
Terima kasih Pak Iqbal. So thank you Professor Naresh for delivering the topic about alkene. We will continue the reaction of alkenes tomorrow. So please make sure that you attend in the class at the same time, 2:40 p.m. Bandung time. And I think today's lecture is enough. Hopefully we can understand we get better understanding about the reaction of alkene. So once again, thank you, Professor Naresh, and see you again tomorrow.
Yep. Okay.
And thank you to all participants. Have a good rest, Professor, and have a good night.
Okay. Bye.
Bye. See you. Thank you.
Bye.
Dan untuk semuanya, terima kasih. Jangan lupa untuk mengisi form kehadiran yang sudah ada di chat. Hatur nuhun, Pak Iqbal.
Sami-sami, Bu Vidya, dan semuanya juga. Ya.
Hatur nuhun, Pak Hayat, Ibu Gebi, tadi ada Prof. Asep, Ibu Amel.
Ada Bu Aisyah kayaknya tadi juga.
Oh, Bu Ai. Hatur nuhun, besok kita lanjut lagi.
Oke, makasih.
Besok teruskan alkena masih ya.